Our next speaker is Alexa Villon of the University of Waterloo, and she'll be speaking on unexpected spatially resolved age, iron, and alpha gradients for the ultra-diffuse galaxy DF44. So have at it, Alexa.
Thank you, and I'd really like to thank the organizers for giving me the opportunity to speak to you all today. And I'd also like to thank my wonderful collaborators listed here, without whom this work would not be possible. So for those of you who are not steeped in extragalactic science, I'm going to start with this figure, which is showing the luminosity on the x-axis versus the radius on the y-axis for a variety of different objects. So in the lower left, we have star clusters like globular clusters. On the opposite end, we have giant galaxies. And all kinds of things in between. The objects that I'll be specifically talking about today are these ultra-diffuse galaxies, which are a seemingly novel set of objects that were discovered in large numbers fairly recently. And the thing that people find interesting about them is, as you can see in this figure, they have sizes similar to giant galaxies, but luminosities similar to dwarf galaxies. And so the initial excitement around these galaxies was the possibility that they might be, quote unquote, failed galaxies. So maybe these were, galaxies that had all the potential to become Milky Way-like galaxies, but for some reason did not. And so there's a lot of interest, particularly in understanding their dark matter halo properties, as this would be an interesting test bed, potentially. And so there was a flurry of follow-up observations and work to try to answer these questions more definitively. And initially, a lot of this work focused on the globular cluster systems. And so here, I'm just, what I'm showing down in the lower right here is for the UDG DF44. And what was found for this galaxy UDG and other UDGs was that these galaxies have overpopulous GC systems compared to what we know about the GC systems of dwarfs of similar luminosities. And this allowed to a development of kind of a toys idea from Eric Peng in 2016 that perhaps UDGs are pure stellar halos, and they kind of revised the failed galaxy scenario from Milky Way galaxies down to more like M33-like galaxies. And I'm just showing DF44 in comparison of, a few dwarf galaxies around M31 and the four next dwarf toroidal, just to give people an idea of what I'm talking about. But this failed galaxy scenario is highly controversial. And one of the aspects of this is that there's actually been this very complicated observational landscape emerging for UDGs, where they really span a range of properties. Some UDGs seem to have perfectly normal globular cluster systems. Some have high stellar velocity dispersion, some have normal. And in fact, all of the UDG formation scenarios that have come out of simulations treat UDGs as just part of the canonical dwarf galaxy population. And so we don't really require any revision or updating to our understanding of galaxy evolution to explain their purpose. But it's still very much a matter of debate. And so one of the ways to get asked to answer and address this issue is to ask ourselves, well, how similar are UDGs to the canonical dwarf population? And the best way to answer that and to get at the evolutionary history of UDGs is through their stellar populations and comparing them to those of dwarf galaxies. And there's been a lot of great work on really detailed characterization of the stellar populations of dwarf galaxies. And there's really two main diagnostics for dwarf galaxy formation. One is what I'm showing on the left here, which is the mass metallicity relation for a variety of dwarfs, including the local group dwarfs and dwarfs in the coma cluster. But really the gold standard is stellar population gradients, which I'm just showing the schematic here on the right of how we typically see stellar population gradients. And the local group dwarf spheroidals seem to have pretty near universal stellar population gradients of positive age and negative metallicity gradients that have informed a lot of dwarf formation scenarios. So when we put UDGs on the mass metallicity relation, we see that there's large scatter, but also UDGs are distant and inherently low surface brightness. So is this just a function of imprecise measurements on metallicity in the stellar populations? And so here in particularly, I'm highlighting the measurement for DF44 from MANGA. And now, but what we were able to do is get KCWI measurements. And so see how, while KCWI lets us measure things like metallicity, so we get significant improvements over signal to noise. And what we see is that indeed DF44 seems to be lower seems to fall below the mass metallicity relation defined by the canonical dwarfs. But of course, what KCWI also for the first time enabled us to get spatially resolved stellar population gradients for UDG. So let's take a look at that. So what we found for DF44 is a pretty flat age gradient, a flat to positive metallicity gradient, and a declining magnesium gradient. And so if we take the schematic that I was showing you before with the canonical dwarfs on it, the local group dwarf spheroidals, and now we put what I've measured for DF44, you see that DF44, in addition to falling below the mass metallicity relation, is also, in terms of gradients, not consistent with the other observations of dwarf galaxies. So in addition, and this is my final point that I'll be making today, is we also know that dwarf galaxies have color offsets between their field star populations and their GC populations, which is taken as a sign that they've were formed in separate star formation events. But here now I'm comparing the magnesium and stellar metallicity measurements for DF44, and we see that the inner region of DF44 matches with the metal poor GCs in abundant space. And so we won't be able to know what this means definitively until we can put actual globular clusters around DF44 on this plot, but this might be a way of trying to time the star formation epochs. They seem to be coincident with metal poor GCs. And so it's kind of now a charged term, but DF44 does seem to be a failed galaxy in that it seems to have quenched early and catastrophically. And that DF44 also does not appear to be consistent with the dwarf galaxy population. And so I think there's still a lot to learn about these galaxies. And I think I'm looking forward to more KCWI data on them. Thank you.
Great, thank you, Alexa. We have time for several questions. So while people are typing in, I'm going to ask, what are the prospects for directly measuring integrated metallicies in the globular clusters of DF44? Are they bright enough you can do with KCWI? Are they?
I'd have to look into that more. There's some spectroscopy for the globular clusters, but it would be interesting to do follow-up work. But DF44 is in the Coma cluster, which is 100 megaparsecs away, so it would probably take a significant investment in time, but it would be very interesting.
And just so I'm clear too, because I don't do this kind of work, are there the metallicies you have are from integrated light of a large number of stars or individual stars that you've somehow managed to pull out?
Oh yeah, so it's extracting the integrated light over different apertures along the radius of DF44. Yeah, good question.
Very good, thank you. We do have a question from Marla Geha asking, did you find any additional faint globular clusters as part of the KCWI observations, and would you have expected to do so given your spatial coverage?
That is a really good question. I know we did not find any additional faint globular clusters around DF44, and I'm not sure if they would be expected or not, but if you want to follow up with me on Slack, I'd be happy to talk more about this with you.
Okay, very good. We have another question from Matt, but we're going to punt that to Slack for now. Thank you very much, Alexa.
Thank you.
And